So, we will continue with what I was doing in the last class, that is the derivation of the equation of change for multi-component systems. And we have seen that by assuming a volume element fixed in space and identifying the ways by which mass of species A can enter the volume element, the reaction which may result in the generation or depletion of A. Together with these two, the mass concentration of A inside the volume element may change. So, what we are doing essentially is writing the species mass balance equation for a volume element fixed in space. And we obtained this expression, the mass balance equation. This is the rho A is the mass concentration of A. The NaX, NaY and Naz are the components of the mass flux vector for component A in the x direction, in the y direction and in the z direction. And this Ra is simply the rate at which A is produced in the volume element as a result of reaction. And we stress once again that this Na contains both the diffusive flux as well as the convective flux, which we have to substitute at some point in future. These are some of the basic relations of which you are aware of, that is, the mass flux is simply the mass concentration times the velocity, and the velocity is expressed, the mass average velocity, the formula for that is this, and you similarly have a formula for the molar average velocity, where the rho's are going to be substituted by C, the molar concentration. So, if I express this equation in vector form, what I would get is del rho A del T plus del dot N A, the mass flux vector, is simply going to be equal to the reaction rate. And if I write, so this is for component A, and I can write the same expression for component B as well, where only this rho A is going to be replaced by rho B and N A is going to be replaced by N B and R A by R B. Once again, I mentioned that these reactions are expressed, the reaction rates are expressed in terms of mass and not for this moment, not in terms of moles. So, these are the reaction rates in terms of masses. So, if you add these two equations together, what you are going to get is the mass concentration of A and the mass concentration of B. So, del T of rho A plus rho B is simply going to be the mass concentration of the solution, which consists of two components A and B. So, rho A, I have used this formula, I have used the relation rho A plus rho B is equal to rho. So, the first term becomes this, and secondly, the sum of mass flux, that is Na and Nb of two species Na and Nb. If you look at the expression of Na and what is the definition of V, then you can clearly see that Na plus Nb is simply equal to rho V. So, rho A Va plus rho B Vb is simply equal to rho, the denominator is rho, so rho times V. So, the equation that we would get is del rho del T plus del dot rho V to be equal to 0. And you can identify this equation, to be that of equation of continuity, which we have written for a pure fluid. So, the equation of continuity which we did write for a pure fluid, and what we are doing here is we have a two component system consisting of components A and B. So, when we write the species balance equation for component 1 and that for component 2 and add them together, what I get is the conservation of mass for the entire solution consisting of two components A and B. So, it should and it did revert to the equation of continuity with which we are familiar with. So, what you get is then is del rho del T plus del dot rho V equal to 0. And if you are dealing with a fluid which is in which the density is constant, it's not varying, then simply this term would be equated to 0, and what you would get is del dot V to be equal to 0. So, this is another form of equation of continuity that we have used extensively in our discussion with fluid mechanics. Here are some of the relations that I once again write for reference. So, this is the mass average velocity. So, rho I V I equals 1 to n, I equals 1 to n, rho I V I by summation rho I. The molar velocity, molar average velocity is C, C is the molar concentration, C I V I times C I. The mass concentration, total mass concentration is rho A plus rho V. The total molar concentration is Ca plus Cb when we are talking about a binary system, and Ca, the molar concentration of A, is simply rho A by Ma, Ma being the molecular weight of component A, and Cb, the molar concentration of B, is simply rho B by Mb. Again, continue with the basic definitions. Na is equal to the mass flux of component A is equal to rho A times Va. The molar flux of component A is Ca times Va, and therefore Na plus Nb would give me the mass flux of the entire solution. So, which would be rho A Va plus rho B Vb, and if you look at this expression, rho A Va plus rho B Vb would simply be equal to V times rho. So, rho times V. So, this follows directly from the definition of V, and in a similar way, if you find out Na plus Nb, it is going to be C, the total concentration in molar terms multiplied by the molar average velocity. So, these are standard forms which we will use subsequently, but I thought that it is important that we have this presented once again. So, if we write the expression which we have obtained before, which is del rho A del T plus del dot N A is equal to R A, all are expressed in terms of mass, and if I divide this equation with the molecular weight of A, that is, if I divide the both sides of the equation by Ma, which is the molecular weight of A, then this equation in mass terms can be converted to molar units. So, in terms of molar units, this equation would simply be equal to del Ca by del T plus del dot Na is equal to Ra. Note that this Ra and everything x in this expression is in terms of molar units. I can write this for component B as well. So, del dot Nb is equal to Rb, which is again in terms of moles. So, when you sum them together, del Ca by del T, sorry, del C by del T plus del of C V star is equal to Ra plus Rb. So, this is the equation of continuity in molar terms. Now, compare the difference between the two equations when we express this in mass terms. This was equal to 0. This is the expression which we have obtained. So, if it's a two component system, so for the mass of A produced must be equal to the mass of B which is consumed. So, in mass terms, the amount produced by reaction and the amount consumed by reaction must be equal. So, mass will always be conserved, but we cannot say that in molar terms. So, not in all cases 1 mole of A is going to give rise to 1 mole of B, which will depend on the stoichiometry of the equation. So, therefore, capital R A and capital R B, the sum of these two may or may not be equal, may not be equal and opposite. So, their sum of R A plus R B in terms of moles may not be 0. So, in order to maintain the general nature of the equation of the relation, underscoring the special nature of capital R A plus capital R B, that being it may or may not be 0, unlike the case of mass expressed in rates expressed in terms of mass, where they always will be 0, I am keeping this Ra plus Rb in the solution as well. So, if we have a system of constant molar density, so this may not be equal to 0, constant molar density, that means C is going to be a constant. So, therefore, you are going to get del dot V star is equal to 1 by C R A plus R B. Since C is a constant, this is going to be 0, this can be taken outside, and del dot V star is this. Compare that with what we have obtained when the mass concentration is 0. So, this is the same thing, these two equations are identical. One is expressed in terms of moles, molar average velocity, molar rate of reaction. Here the expressions are in terms of mass. So, they are similar in concept, but different in form. Next comes the what is going to happen to Na. We have said that Na contains both a convective contribution and a conductive contribution. Same applies for capital Na as well. So, if we write Na in terms of the mole mass fraction Wa, then the Fick's law would be Wa times Na plus Nb is equal to minus rho dAb times del of omega A. So, this is again this is mass fraction. So, we are writing this equation in Fick's law, the generalized Fick's law in terms of mass fraction. This is mass flux, mass fraction, mass flux, constant density, dAb, and mass fraction again. And if you write in terms of mole fraction, if I write in terms of mole fraction, we get the familiar equation. So, mole fraction is we denote by Xa, and the familiar expression is Xa times Na plus Nb equals minus C dAb del of Xa. Okay. So, again these two equations are identical. We have so far used this form of the Fick's law, where the diffusive flux, where we have the diffusive flux and this is the bulk flow term. So, it the same as this except the difference between mass and moles. So, the two equations which we have in here, this equation in terms of mass and this equation in terms of moles, and what we are going to do is we are going to substitute small na and capital Na in these equations, small na over here and capital Na over here, these two equations in that, and we would obtain two identical equations, completely equivalent equations, not identical, equivalent equations. One is in terms of mass, this is in terms of mass and mass fraction, in terms of mass and mass fraction, and in terms of moles So, fundamentally there is no difference between these two. One, as I said, is in terms of mass, the other is in terms of moles. This is mass average velocity, this is molar average velocity. This is rate of generation of A in mass per unit time, this is rate of generation of A in moles per unit time. So these are identical equations, but we should also point out there are certain limitations, certain things that we have assumed which must be mentioned. We said that the diffusion takes place only when there is a concentration gradient present in the system, but there are other ways by which diffusion can take place. If you have temperatures different between 2 points in an otherwise in a solution where the concentrations are the same, but the temperatures at 2 points are different, that could also create a diffusion. If you have a system, if you have other parameters are different in a perfectly in a solution which has the same concentration everywhere, then also you can have diffusion, because diffusion, if you use the term strictly, is not dependent on concentration gradient alone. Diffusion is going to result if there is a chemical potential difference between 2 points in a solution. The true definition, the true cause of diffusion is not only concentration difference, though that is the most common cause of diffusion, mass diffusion. Actually, it is the concentration the chemical potential difference which causes a species to move from one point to the other. And chemical potential is a complex function not only of concentration but also of pressure and temperature. So if concentration being equal at every point in a solution, if the pressure and temperature vary in between 2 points in a solution, even if the concentrations are same, we can still have diffusion. But in our analysis, what we have presented, we did not consider the diffusion induced by temperature or by pressure. So the expression that we have obtained is only for concentration difference induced diffusion only. So this restriction or this limitation of the equation should have to be kept in mind. Though it is going to be the diffusion, the concentration difference is the most common cause of diffusion, of movement of species from one point to another. So these are the two equations, and I am going to write these expressions once again. These are called the special cases that we encounter. The first equation, which is del rho A, the first equation that we have written, plus del dot rho A V is equal to del dot rho dAB times the del of the mass fraction plus R A. So if I just expand this term, what I expand this term and assume that dAB is a constant. So for the case of constant total mass concentration of the solution and constant dAB, this expression would be simply del rho A del T plus rho A times del V plus V times rho A, and this, since dAB and rho both are constant, so it can be taken outside. So dAB is taken outside and rho is taken inside. This is mass fraction multiplied by the total density. So this would simply be equal to del square times rho A plus R A will remain unchanged. So I expanded this into these two terms, took dAB outside and took rho inside. So the mass fraction would simply be equal to the mass density. Mass fraction multiplied by the total density would simply be equal to the mass density of component A. And we know that for a constant rho system, this is equal to 0 from our equation of continuity. So what we have then is del rho A del T plus V times del rho A is equal to dAB times del square rho A plus Ra. And when you divide by the molecular weight of component A, if I divide this term, this equation by the molecular weight of component A, what I am going to get is del Ca del T plus V times del Ca is equal to dAb del square Ca plus Ra. So, these are in mass terms and this is in molar terms. So, these are identical equations. Conceptually they are the same, but one is in mass concentration, this is molar concentration, molar concentration, molar concentration, reaction rate expressed in terms of moles rather than molar concentration expressed in terms of masses. So, if you look at this expression a bit more carefully and if you see what is this, this is nothing but the substantial derivative of concentration of A. So, what I have in, if I would like to compare this with the equation which we have obtained, and I hope you remember this as dt by d temperature by d time equals K del square T plus some sort of a generation term. If you divide both sides by rho Cp, what you get is dt by d time is equal to K by rho Cp, and K by rho Cp is nothing but your alpha times del square T plus S prime, where S prime is simply S by rho Cp. So, when you compare these two terms, these two equations, or rather these two equations, what you have here is the substantial derivative of concentration, what you have here is the substantial derivative of temperature. What is on this side is the transfer of mass A, species A, as a result of diffusion. This is transfer of energy through conduction because of a difference in temperature. So, this and this are identical. This is a generation term through reaction and this is energy generation. It could be of various means, a nuclear source, a current source which is resulting in heat and so on. So, the two equations fundamentally conceptually are then identical, and this is the beginning of simultaneous identical treatment of mass transfer and heat transfer process. So, the mass transfer and heat transfer process, the form of the governing equation, the forms are absolutely the same. Conceptually, one is the substantial derivative of concentration, this is the substantial derivative of temperature, this is the diffusive transport of mass, this is the diffusive transport of energy, this is a source term due to reaction, this is a source term due to it could be by various means, that is nuclear, ohmic and so on. So, if the governing equations, the same form of governing equations underscore the fact that it is possible to treat mass transfer and heat transfer together. So, in many cases, in many situations where a simultaneous heat and mass transfer is taking place, the form of the equations governing the heat and mass transfer will be the same, and we will see special cases where not only the forms are the same, but the boundary conditions expressed in dimensionless forms will also be the same. So, if that situation happens, that is the governing equations are the same and the boundary conditions in dimensionless forms are the same, then a significant simplification of the entire process can be obtained, which we will study when we are going to explore the analogy between heat, mass and momentum transfer. But it would be sufficient here to mention or to underline the same form of the equation, same form of the equation of heat transfer and equation of mass transfer in these cases. So these two equations are to be kept in mind, the similarities between them when we are going to solve for problems. So this is the starting point for simultaneous heat and mass transfer. So whenever we deal with simultaneous heat and mass transfer, we have to think in terms of the similar nature of the equations. So coming back to the equation for mass transfer, what we have then is del Ca del T plus V times del Ca is equal to dAB del square Ca plus a reaction term when everything is in terms of moles. So this equation has this equation can therefore be found, it's the form of the equation in Cartesian coordinates, in cylindrical coordinates and in spherical coordinates. So you choose the equation and its form and cancel the terms which are irrelevant. What you get is your governing equation. So in the next part of the next class, what I am going to do is I'll show you a problem which is difficult to visualize when you try to do a shell mass balance. But the problem, and getting to the governing equation is a lengthy exercise. But if you do that with this equation, the generalized species transport equation, how easy it would be to get to the final form of the governing equation. So in the remaining 2-3 minutes that I have for this class, I will simply introduce the problem and show you what kind of a shell one has to assume in order to obtain the governing equation, and then in the next class I will show you how to use the species balance equation to solve for the problem. So the one that I am going to do right now is so this is a solid wall and a liquid film is falling along the solid wall, okay, and there is a species. So this is liquid B and liquid A gets dissolved. So at this point, from this point onwards, the falling film of B sees the component A. So if we talk about this being the Z direction, this being the X direction, and this being the Y direction, then at Z equals 0, so this is Z equals 0 and we have Z equals L. And we will assume that the film is wide enough such that none of the parameters are going to be a function of y. So as the film falls, it sees component A only at z equals 0 up to z equals L, and this component A gets dissolved in the liquid B, and let's assume that it's I do not make any comment on whether A is sparingly soluble or highly soluble. The moment an A molecule gets dissolved, it starts its downward journey. but there is a difference in concentration in this direction. So A must diffuse in this direction and A is going to go in this direction by convection. And we are going to assume that I have only one component of velocity Vz which is not equal to 0, but both Vx and Vy are equal to 0. So it is a one dimensional motion of the liquid that after A gets dissolved carries it in this direction, and this distance, the thickness of the film is delta. So you have no A present in it, some A present up to this, and the penetration of A inside the liquid film will keep on increasing as we move in this direction. So some sort of a profile of A is going to be felt, is going to be developed in here. I would like to find out how much A is going to get dissolved in liquid B when it falls with, so you have a velocity Vz. I would like to find out the variation of Ca, and I understand the concentration of A is going to be a function of x, it is also going to be a function of y. So it is going to be a function of x and it is going to be a function of y. So I would like to find out the profile of A in the liquid film. So A, profile of A in the liquid film. Okay. And we understand there is a diffusion in this process, and convection in this process. So if I, this is my diffusion in the x direction, I have diffusion in the y direction, and I have convection, sorry, in the z direction, Ca, I am sorry, Ca has to be a function of x and z. So these three are taking place. The question then comes, how am I going to take a shell? Because we generally take a shell, is it going to be of size delta x, since Ca is a function of x, or is it going to be of shell delta z, since Ca is a function of z? So what is going to be my shell, of delta x thickness or delta z thickness? And you can clearly see, since Ca is both a function of x and z, the shell that you are going to design is going to be a function both of x and of z. So therefore this the shell that you are going to do is going to be a shell like this, which is delta z, and a shell like this, which is going to be delta x. So this is the shell across which you are going to make all the balances. So your shell is going to be of area del x, del z, and it could be of any y, it does not matter. All the parameters are going to be a function of del x and del z. Del y is not relevant. Now you see the problem. So far you are dealing with a shell with one dimension. Now you have a shell in which the smaller dimension could be 2. So instead of a thin page type shell like this in del x or in del z, now you have a shell which has some del x and some del z. How do you do that? You can still do it. You can still do it, but you have to mentally visualize through this phase I am having conduction and convection both. Through this phase, since there is no velocity, this is my film. Through this phase, since I do not have any velocity, any bulk velocity, I am only having conduction. So, the top faces of the imagined shell will be exposed both to conduction as well as to convection. The side face of the shell is only exposed to diffusion, and in this way, in the y dimension, it's not going to be, it's not relevant, since nothing, the concentration is not a function of y. So, for a two dimensional system, your entire shell momentum balance starts to break apart. Now, consider this to be a situation in which the transient effects are added to it. How the complexity increases when you start having a velocity or a concentration which is dependent both on x and y and as well as t. If you look at your textbook Bard Stewart Lightfoot, this specific problem has been done using a shell balance, shell species balance. So, it still you would be able to visualize it, but since you know the species balance equation, what am I going to do in the next class is solve the same problem, but start with the species balance equation and cancel the terms, and you would see what has required one page of the text and some visualizing, imagining of the different transport processes on an imaginary shell. How easily it can be done when you pick the right component of the equation and cancel the terms which are not relevant in this specific case. So, this is the one which you are going to see in the next class.